Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at the inner product for finite dimensional vectors. So in this topic, we will define the inner product for finite dimensional real vectors first. We will then consider some of the properties of the inner product. We will then define an appropriate inner product for finite dimensional complex vectors and look at the properties here. We will conclude by defining an inner product space. So, if two vectors, u and v, are both in R to the n, we will define the inner product of these two vectors as the sum of the element-wise products. So this is going to be the first entry of u times the first entry of v plus the second entry of u times the second entry of v, and so on and so forth. So, for example, if I have these two vectors in R3, then we note that the inner product is just the product 3 times 1 plus negative 5 times 4 plus 2 times 6, and that's equal to 6 minus 20 plus 12, which is equal to negative 2. So what are some of the useful properties of the inner product? First of all, here's the definition of the inner product. But notice that in the sum, it's just a multiplication, and multiplication is commutative. So we could just rearrange those two entries. So that is equal to that sum of products. But that, by definition, is the inner product of v and u. Thus, the inner product is symmetric in its two operands. Remember that we described the equality operator as being symmetric. You'll recall that x equals y if and only if y equals x. Okay, next property. Here's the next useful property. Recall that if I multiply the vector u by a scalar alpha, this just multiplies each entry of u by that scalar. So when we're calculating the inner product, we're just multiplying each term of the sum by alpha. But that means that alpha is a common factor, so we can factor out the alpha. But wait a second, this is just alpha times the inner product of u and v. Nice. Similarly, if I have a sum of two vectors in the first operand, then recall that the entries of this sum are just the sum of the corresponding entries in the two vectors. So therefore, the first entry of this sum is the first entry of u1 plus the first entry of u2. In calculating the inner product, this will be multiplied by the first entry of v. Okay, so now we have a sum multiplied by v sub k. But field multiplication distributes over addition, so let's do that. And now we have a sum of sums. Well, a sum of sums is equal to the sum of sums. Well, that just sounds really bad. But really, that's all we did. We're just going to split it up into two sums. Now, if you'll notice, the first sum is the inner product of u1 and v, while the second sum is the inner product of u2 and v. This second property is usually summarized as a single expression. The inner product of a linear combination of vectors and v is equal to that same linear combination of the inner products of those vectors inner producted with v. The same is true for the second operand. Consequently, because the inner product is linear in both the first and second operands, it is described as being bilinear. That is, it is linear in both operands. Now, here's a third product. If we take the inner product of a vector u with itself, notice that this looks vaguely familiar. It's the sum of the squares of the entries of u, and this is a value that must be greater than or equal to 0. You'll also notice that the inner product is equal to 0 if and only if u is the 0 vector. And if you can't see this, go back to the discussion on the 2 norm, and you will see that the proof will be more or less analogous. This property of the inner product is described as being positive definite. That is, the inner product of a vector and itself is always greater than or equal to 0, and it is definitely positive if u is not equal to the 0 vector. Thus, to summarize, here are the 3 properties of the inner product for real vectors. Now, if u and v are complex vectors, can we define the inner product in the same way? Well, if so, let's consider this one here. We have the vector 1j. So the inner product of u with itself is 1 times 1 plus j times j. 1 squared is 1, but j squared is negative 1, so this is equal to 1 minus 1, which is 0. And this is frustrating because now we lose positive definiteness. In fact, the vector 0j inner producted with itself would be the value negative 1. So now the inner product of a vector and itself is not even positive. Now, if we're trying to define angles, this is going to be an issue because a vector should be pointing in the same direction as itself. So this is not going to work. We need that positive definite property. One way to get that positive definite property is to redefine the inner product so that you're taking the complex conjugate of the entries of u and multiplying them with the corresponding entries of v. Thus, if we have a single vector, we thus have that the inner product of u with itself is the sum of u sub k star times u sub k. But this is just the absolute value of u sub k squared. So this is a positive number. A sum of positive numbers is positive. And you will see once again that this can equal 0 if and only if u is the 0 vector. All right, let's do an example here. We have 2 complex vectors here. So the inner product is the conjugate of the first one entry multiplied by the second entry, corresponding entry in the second vector. So let's first calculate each of the 3 complex conjugates. 1 plus 4j becomes 1 minus 4j, 2 minus 3j becomes 2 plus 3j, and 5 minus 2j becomes 5 plus 2j. Now let's calculate each of those 3 products. So the first product is 13 plus 16j. The second one's a little simpler. It's 8 minus j. And the last one is 30 minus 10 plus 25 plus j plus 12j, which is plus 37j. Summing up these three complex numbers, we get that the answer is 41 plus 52j. So the properties of the inner product for a complex vector space are slightly different. Because we are taking the conjugate of the first entry, then we now have something called conjugate symmetry. The inner product of u and v is now equal to the conjugate of the inner product of v and u. It is not bilinear anymore because now if the scalars in the linear combination of the first vector are complex, when they come out of the inner product, we will actually be taking out their complex conjugates. So this is described as sesquilinearity. Sesqui means 1.5 in Latin. So it's not quite bilinear, it's just less than bilinear. However, fortunately, the inner product is still positive definite, so that is good. Now, a vector space that has an inner product defined on it is often called an inner product space. The assumption is made that it must be a valid vector space. Now, one small comment on notation. Physicists and engineers define the inner product for a complex vector as follows, where the first vector is conjugated. For whatever reason, a lot of mathematicians define the inner product for complex vectors as having the second vector being conjugated. It really doesn't matter because where it does count, that is, when the inner product is 0, both give the same result. Okay, so following this topic, you now know the definition of the inner product. You also know that the properties of the inner product, and you are aware that there's a subtle difference between the inner product for real and complex vectors. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!